Okay, so what I want to do now is take a look at three different queuing systems, and each of these systems has a model that can be solved analytically. Again, complicated queuing systems like with multiple queues feeding each other, multiple workstations feeding each other, can't be solved analytically. They must be solved using a simulation model. But these simple models we're going to look at here can be solved analytically. And we're going to start out with the simplest of these models, which is the MM1 queue. So remember that using Kendall's notation, this represents the arrival process, this represents the service process, and this right here is how many servers we have. So we can see that the MM1 queue has exactly one server. Okay, but then what's the M stand for? Well, M stands for Markov. Okay, and a Markovian process is basically Poisson process. So we're talking about a certain type of random variable for generating both the arrivals and the service times. So the big M tells us we have a Poisson arrival process, and the second big M here tells us we have a Poisson service process. So what does that mean? That means that we've got a fair amount of variability in our arrivals as well as a fair amount of variability in our service times. And it's perhaps a little less common in service times, but it's pretty common for arrivals to actually follow a Poisson process. If you think about watching an ATM machine or some other single server system, all of a sudden a bunch of people will arrive, and nobody will arrive, and one person will arrive, and a bunch of people will arrive again. So there's a lot of variability in arrival processes when people are coming from a wide area to a single a service system, such as people coming from the neighborhood to an ATM. The actual arrival process tends to be like a Poisson process. Service processes may be a little less likely to be Poisson, but there are some highly variable service processes out there, and actually an ATM machine is a good example of one. Some people know exactly what they want to get from the machine and have no trouble reading the instructions. Other people seem to have all kinds of problems using a machine and take a long time. So if you have highly variable arrival processes, which is pretty common, and highly variable service processes, still somewhat common, this is a good model to use. Now, assuming here we have infinite system capacity, and we have this additional information about the arrival and the service rate. We use this symbol lambda, that's a Greek letter, and yet another Greek letter, lambda. It's a standard symbol for the arrival rate of a queuing system. So we're saying that we have an average arrival rate of customers to the server, and our example here is going to be 8 per hour. And this looks like a U, but it's really a lowercase Greek m, so it's mu, and that's the average service rate of customers by our server. And in our example here, our server can serve 10 per hour. So if we know that the arrival and the service processes are Poisson, then we know a lot about those processes, and all we need to know to completely characterize both of those processes is the average rate of either arrivals for the arrival process or number being served per hour for the service process. Well, if we know lambda and we know mu, we can calculate yet another Greek letter here. A rho looks like a P, but it's a lowercase Greek r. We can calculate rho, the traffic intensity. A rho is simply the arrival rate divided by the service rate. In our example here, that would be 8 over 10, or 0.8. So traffic intensity, just basically showing you how heavily utilized is your system. The bigger the traffic intensity, the more heavily utilized the system. If the system has infinite system capacity, like our system does here, then the traffic intensity cannot get above 1, because if people are arriving faster than they can be served, then that means the line just explodes and fills up the entire planet. Not realistic. So for these sorts of models with no system capacity, they only make sense when we have traffic intensity less than 1. And again, in our example here, the traffic intensity is 0.8. Well, we can calculate the performance measures using the following formula. These are also provided in the book. And let's start down here, actually. The average number of customers in the system, we can find that simply by taking rho and dividing by 1 minus rho. So we've already found the traffic intensity to be 0.8, so 0.8 divided by 1 minus 0.8 gives me an average number of people in the system equal to 4. So on average, there'll be 4 customers both waiting to be served and being served. Once I find the average number of customers in the system, I can take that number and feed it into the formula to calculate the average time spent by a customer in the system, because that is simply equal to the average number of customers waiting divided by the arrival rate. So if there's 4 customers on average in the system, and there's 8 customers arriving per hour, then the average time spent by a customer both waiting and being served is 4 divided by 8 equals 0.5. That's half an hour, or 30 minutes. Well, once I've got this time, then I can calculate the average amount of time spent by a customer just waiting, because all I do is I take the average time in the system and I subtract out the average time in service. And since the service rate is mu, the average time in service is simply 1 over mu. That is, if the average, if the service rate is 10 customers per hour, then the average service time per customer is 1/10 of an hour, or 6 minutes. So to calculate W sub Q, I simply take my average time in the system, 0.5 hours. I subtract out 1 over 10, 1/10 of an hour, and I get 0.4 hours, or about 24 minutes, as my average time spent waiting. I can then use this number, you can see all these numbers are related, to help calculate the average number of people waiting in the system. I simply take the average time waiting times the arrival rate, and that gives me my average number of people waiting. So I take this 0.40 that I just calculated, multiply it times my average arrival rate of 8. 0.4 times 8 is 3.2 people waiting in line on average. So my 4 measures here are all related, and again I could combine these using algebra. I could come up with different expressions for these 4 performance measures, which are equivalent to the ones I have here. I think these are some of the easier ways to present this information, but it does mean that if you want to find the average number of people waiting in the system, you got to do some other calculations first. Now, the one performance measure I haven't talked about yet is up here, and that is the probability that there are n people in the system. To calculate that, I first have to find the probability that the system is empty, the probability that there are exactly 0 people in the system, and that's simply going to be 1 minus traffic intensity. So 1 minus 0.8 gives me 0.2. I got a 20% chance, or a 1 out of 5 chance, that there's nobody in the system. Once I got that number, I can feed it into this formula and find the probability that there are n people in the system for any value of n. It's simply going to be the probability that the system is empty times rho, that's rho there, to the nth power. So if I want to know, for example, the probability that there is exactly 2 people in the system, I take p sub 0, which is 0.2, times rho squared, that's times 0.8 squared, and I get not quite 13%, 0.1280. That's a lot of math all on one page. One last thing, I can do this calculation for other values of n, and I did them in a spreadsheet, and we can see how that looks over here. Basically, for larger values of n, the probability of there being exactly that many people in the system gets smaller and smaller. So there's a 20% chance of there being nobody there, a 16% chance of there being exactly 1 person 12.8% chance of there being exactly 2, so forth and so forth, but there's only just barely a little over a 5% chance of there being exactly 6. If I wanted to know the probability of there being, say, less than 2, then I have to add up probabilities, right? Again, you remember that from your probability and statistics class. So the probability of there being less than 2 people in the system is the probability that there's either 0 or 1, because that's the only way there can be less than 2. The probability that there's either 0 or 1 is 0.2 plus 0.16 or 0.36. So there's a 36% chance that there's less than 2 people in the system. And of course, since all the probabilities, including the ones I haven't shown here, have to add up to 1, there's a 1 minus 36% chance, or 64% chance, that there's 2 or more people in the system. Well, let's take a look at how our simple system performs as the traffic intensity increases. So let's suppose that we had the same service rate. We could serve 10 people per hour, but suppose that the average arrival rate changed throughout the day or from season to season. And as the average arrival rate changes, as it goes up, the traffic intensity will go up. As it goes down, the traffic intensity will go down. So right now, with an arrival rate of 8 people per hour, that puts us right about here. And we saw that the didn't draw that real straight. We saw, going back to the previous slide here, that the average waiting time in the system was 0.4 hours. 0.4 hours is 0.4 times 60 is 24 minutes. And that's what that should represent right there. Again, it's sort of hard to see it with my drawing. What happens if the average arrival rate went from 8 per hour to 9 per hour? Okay, then we're over here. We got a traffic intensity of 90%, and our wait time has jumped up almost to an hour. That's not good. That's going to be turning away some customers. And if we were getting, say, 9.5 customers per hour, well, then the waiting time just goes through the roof. You can see that the closer we get to 100% utilization, our waiting time goes up to almost, well, it goes over 2 hours, which is, of course, ridiculous. Customers just aren't going to wait that long for most services. So you can see that it's not a linear relationship here, and we need to be careful about having too high a level of traffic intensity or too high a level of utilization of our system. So we want to keep our traffic intensity probably below, not much above, certainly 80%.